The vastness of scientific information can cause us to look up at the stars with awe, but can also cause other reactions, like skepticism and disbelief, denial and discomfort, and even fear. On this season of the Omnia podcast, we talk to scientists and other scholars about scientific ideas that cause big reactions. We'll look at stories of science getting knocked around and standing back up again in a world full of polarization, politics, misrepresentation, and simple misunderstanding. Welcome to In These Times, Fear and Loathing, and Science. Our final episode is about climate change. It's come up a lot this season. It's been in the news, too, as the 2021 United Nations Climate Change Conference in Glasgow made headlines around the world.
World leaders are in Glasgow for that historic climate summit, COP26. It's been billed by many as the last best chance to save humanity.
It's 1 minute to midnight on that doomsday clock, and we need to act now. If we don't get serious about climate change today, it will be too late for our children to do so tomorrow.
The conference highlighted the urgent need to limit the planet's warming to 1.5 degrees Celsius, or 2.7 degrees Fahrenheit, by 2100. If temperatures get any higher, scientists predict dire consequences, including the increase of storms, floods, and other weather events once thought rare. Our planet is 4.6 billion years old. It's been through a lot of changes in that time, from ice ages to periods of extreme heat. The scale of those changes is sometimes hard to grasp. It's also hard to truly understand what our world may look like in the future, and how our actions now have far-reaching impacts. Welcome to Episode 7, Climate Change and the Problem with Time. To get started, let's talk about how we know what we know. Irina Marinov is an associate professor in the Department of Earth and Environmental Science at Penn. She is an oceanographer and a climate modeler.
I grew up in Eastern Europe, in Romania, and I noticed early on the environmental destruction that the collapse of communist industry brought with it. I somehow always knew that I wanted to save the planet. And science was a natural fit to me, so I arrived at physics as a first step, and then later on in graduate school, I went to climate sciences.
Professor Marinov is an expert in climate modeling. Climate models allow scientists to make predictions about how lands and oceans will be affected by things like rising temperatures and carbon output.
Climate models, how do climate models work? Climate models, also known in our jargon as general circulation models, or GCMs, use mathematical equations to characterize how energy, water, and gases, such as CO2, for example, interact in different parts of the ocean, atmosphere, and land. We use these equations to represent well-documented processes, physical and chemical processes, for example, conservation of energy and conservation of mass, but also how water, wind, nutrients, and gases move with air and water currents. We have equations in these models not only for the physics of the ocean, but also for the nutrients and chemistry, both for the ocean and for the atmosphere. Models are becoming more and more complicated as our knowledge of chemistry, biology, and physics improves. But the interesting things that not many people know is how interdisciplinary the expertise needed to run a climate model is. What we do with models typically is, first of all, you put all these equations in and then you want to test the climate model. You can run the model from the past to the present time, and then you compare it with observed climate and weather conditions over, let's say, the past 100 years. And this allows you to check the accuracy of the models and, if needed, to revise them. Then what you do is, first you compare your model output to observations, and then you compare with results from other models. And once you're satisfied that your climate model performs well in this testing, you start to think about simulating the future climate.
Once scientists test the climate models against what they know about the past, they can run models for future scenarios. Professor Marinov focuses the majority of her research on the ocean. understanding the ocean is key to understanding climate change, because oceans absorb more than 90% of the excess heat we put in the atmosphere.
The ocean, because of its huge size, regulates very much the heat budget on our planet. The next point and the next number that comes to mind is that in the past few decades, the ocean has absorbed around 30% of all the CO2 emissions from human activities. So of every 100 molecules of CO2 that we put in the atmosphere, about half or 45% stay in the atmosphere, and the rest is divided approximately equally between land and the oceans. So again, the oceans have a very big impact on carbon cycling. So they take up CO2 and they take up heat, basically mitigating climate change.
But that mitigating effect has its limits.
Part of what we're seeing is sea level rise. Next, we're seeing melting of sea ice, particularly in the Arctic. The Arctic is warming much faster than the rest of the planet. We are seeing the large-scale circulation changes in the ocean. As an example, our models predict that the Gulf Stream will slow down into the future because the North Atlantic, where the Gulf Stream sinks, is becoming warmer. Therefore, the entire prediction is that as the high latitudes are warming and freshening with more precipitation and more ice melt, we are going to slow down the large-scale circulation of the ocean. This will have impacts on nutrient patterns, it will have impacts on carbon uptake by the ocean, and it will have large impacts actually on ocean ecology.
In addition to oceanography and climate modeling, Professor Marinov has recently started to study climate change denial.
There's good news and bad news on this topic. So the UN Development Program, the UNDP, has recently commissioned a study called the People's Climate Vote. It's an Oxford University study that was released this year in 2021. They polled through advertisements in mobile games in many languages, 50 different countries. And they'd asked to question public opinion on the climate emergency. The good news is that when analyzed across many regions, the proportion of people who believe that climate change is an emergency is pretty high across the world. And what's interesting is that GDP seems to matter. So the public belief in the climate emergency is higher in high-income countries compared to middle-income countries and then compared to least developed countries. That's the good news. The bad news is that among the high-income countries, the US is at the bottom.
Professor Marinov notes other interesting facts about climate change denial. In the United States, Canada, and Australia, women and girls believe in the climate emergency at higher rates than men and boys. And in the US, unlike in most other countries, a person's level of education does not always influence their belief in or understanding of climate changes. Instead, political leaning is the biggest influence. She is concerned by this finding.
It's a huge separation. This divide of opinions takes precedence over education, gender, and anything else. It's quite astounding, and I want to study more, but I doubt that anywhere else in the world we're going to find these kind of separation with politics, which is puzzling to say the least, and absolutely needs to change because naturally there is no connection between climate change and politics. There should be no connection between climate change and politics. The ocean is the ocean, regardless of your political color.
While Professor Marinov studies oceans, Jane Dmochowski, senior lecturer in Earth and Environmental Science, focuses on Earth.
So how is Earth's vegetation climate changing with our climate? It really varies depending on where you are. In general, it's definitely changing. Some places are getting wetter and that vegetation is getting greener. In some cases, we can see evidence of plants that only really thrived in relatively warm environments, moving farther north and farther south toward the poles. And obviously, as we're all very familiar with droughts, in California and Colorado and the western United States, we know that a lot of vegetation is becoming much drier in places where it used to remain green for a longer amount of time, becoming much drier and also much more susceptible to fire.
Tonight, a growing threat as the giant Dixie Fire carves a destructive path, now the largest single wildfire in California history. The massive inferno, driven by historic drought conditions and winds fueling a blowtorch.
Like all scholars in this episode, Professor Dmochowski's interest in her field grew out of personal experiences. When she was an undergraduate at University of California at Santa Barbara, there was an earthquake. That's not unusual for the area because Santa Barbara lies near several fault lines. A U.S. Geological Survey study has predicted there is a 70% chance of a magnitude 7 or greater earthquake occurring along the San Andreas Fault by 2030. When she was in college, Professor Dmochowski wanted to understand the Earth around her and the plates beneath her. Now, she studies vegetation's response to climate change using remote sensing imagery. She wants to help her students understand the Earth, its past, and its future. Going on a fact-finding mission about the Earth's 4.6 billion year history is a big task, but scientists know how to get answers.
So we have a lot of information that helps us to understand Earth time. And one of the ways that we understand Earth time and understand, different times along Earth's timescale is with radiometric dating. So most people are familiar with what we call carbon dating, so using the carbon isotopes to date maybe artifacts or things like that. That has a relatively short decay, it's a short decay system. But most of the time for geologic timescale, we use isotopes that have much longer decay systems, like uranium to lead or potassium to argon. And we use these to then date rocks, and that's where the age of the rocks in Earth's timescale, that's how we get those times.
Scientists know the Earth has gone through a lot of changes in its long life. A lot of these changes are recorded in the Earth itself, in dirt, rocks, oceans, and trees.
And so when we look at a rock, oftentimes we see layers of rock as those sediments over time have deposited one on the other and created what we call beds of sedimentary rock. And we can look at those and, with radiometric dating, we can determine ages, but we can also determine things about the environment at that time. So were the rocks deposited in water? Were they deposited by wind? Were there animals living in that environment? Would you find, if you found fossils, what types of plants were living in that environment? Was it if it was fluid environment, was it really turbid? Was it fast moving water, or was it very, very still water? Things like that we can determine from the rocks really help us to reconstruct Earth time.
Knowing the Earth's age and timeline is one thing. Understanding it is another.
So in classes, I like to use a ball of yarn, and I say, ahead of time, I've measured out this ball of yarn. So I can give the students a one-to-one of what is an inch of this yarn compared to an amount of time. A couple things that strike students typically is that you go through a lot, 70% of this ball of yarn before there's any real, life that they've heard of, or even things occurring in Earth that they think of as really ancient history haven't even happened in that first 70% of Earth time. Another thing that they are always struck by is just how close to, the point where I say, that very last thread of yarn that is human civilization. It's usually not, depending on how long my ball of yarn is, it's usually not that far since, dinosaurs had just become extinct. And I think oftentimes they'll think of dinosaurs as the beginning of time, or, really, really ancient history, when in the grand scheme of Earth time, they're really much closer to our current time than they are the beginning of Earth time.
But you're not sitting in Professor Dmochowski's class looking at a ball of yarn. You're listening to a podcast.
If you don't have the ball of yarn in front of you, though, I think the best representation is really more of, a calendar year. So if we sort of went to a calendar year and walked through our geologic time, we would then, at the very, very end, it would take the entire calendar year, get to just the last final minute before we actually had human civilization, and what we know is sort of the industrial age, just the last second of that calendar year.
Understanding the Earth's past and caring for it in the present can protect its future. That kind of long-term thinking is hard, but Jared Farmer says we're up for the challenge. Professor Farmer, Walter H. Annenberg Professor of History, is an environmental, place-based historian. He studies how non-human things affect human history. Things like, say, a virus. By now we're all familiar with how much those can alter our lives. But also things like mountains, rivers, and trees. Professor Farmer recognized the relationship between land and people as a child growing up in Utah.
The most famous historical saying in Utah, supposedly uttered by Brigham Young, second prophet of the Mormon Church, is, "This is the place," right? So that's the culture I grew up in. It's like, this is the place. So it's like, maybe it was inevitable that I became a place-based historian. I was just trying to understand, what is a place and how does one make a place? I mean, places are not created by nature, right? They're not created through geological forces. Places are landforms, landmarks, landscapes imbued with human meaning, right? That's what a place is. It's a site of concentrated human meaning. And so there's always a history to a place.
Professor Farmer has written books on rivers and mountains, and his next book focuses on trees, ancient trees, to be exact.
In my new project that I just finished, that will be out next year, I'm trying to kind of take that place-based environmental history approach, but to zoom out to the planetary. And so that's the tricky part, is I'm trying to do a place-based planetary history, which is different than global history. It's different than a history of globalization. And it's not like an Earth history the way that maybe an Earth scientist or geology would, but I'm trying to get at these very large-scale planetary processes through very specific, indeed hyper-local sites, places, individual trees. So basically my book is about individual ancient trees all around the world as sites that attract religious thinking, sometimes nationalist thinking, but also scientific thinking. So I'm really interested in this overlap of history of religion, history of science at ancient trees. And so these ancient trees are a way for me to think about these longer units of time, these kind of millennial, multimillennial units of time.
Professor Farmer says that even before scientists could date ancient trees, people had a certain reverence for them and a protective instinct. Communities dated trees by what he calls relational age, saying things like, that tree is as old as the temple. Dendrochronology, or tree ring science, made ages exact. And like rocks, trees can help us tell time. And we're not talking about a single lifetime. We're talking about deep time beyond the scale of human life. Professor Farmer wants us to take long looks back in time and then long looks forward.
I think with climate change, we need to recultivate the arts of long-term thinking, which is in our history, right? If you think about cemeteries, if you think about genealogy, you think about religion, these are all practices of long-term thinking, right? It's in our history, it's in our past. People are good at long-term thinking, right? I think it's just that in my lifetime, the emphasis has been so much about faster, cheaper, crappier, right? Just shorter. Short time has become everything. Even, long-term shareholder value is incredibly short if you think of it. So I guess with trees, I'm just trying to remind people of these existing cultural traditions all around the world of thinking in the long term, and how people have already been doing this with trees, have been doing it with universities, right? There are many universities that are hundreds, even over 1,000 years old. But also there are these relationships that people have with trees that are extremely old. And the trees themselves, the specimens themselves are often hundreds or thousands of years old, but then species or the genetic lineage is often exponentially older than that.
For Professor Farmer, trees offer an emotional access point.
People have deep feelings about trees. There are all these like mythologies about trees. There are famous and iconic and emblematic trees all around the world, protected trees, national parks, natural monuments that protect trees. Trees are tourist sites. Trees are on, flags, T-shirts. I mean, it's very common, right, for people to love trees, to hug trees. I've never met somebody who hates trees. You might hate a specific ginkgo, a female ginkgo, perhaps, if it's in front of your house. But in general, like, people love trees. And so I think because there is that kind of built-in emotionalism about trees, in part because people personify trees, that is a great way to kind of introduce people to this concept of long time, which itself is an introduction to deep time. And so I'm trying to kind of just work with kind of some existing, very deep kind of human traditions of veneration for old trees by appreciating our long-term relationships with long-lived beings. We can remind ourselves of our own ability to think and live in the long term and maybe achieve a better balance between, again, living as multi-temporal beings. And I think that's just like so important right now, because not only do we need to live in the past and the present and the future, we have to extend that future into the deep future, right? Because we are making changes that will last for millennia. And so how do we do that? How do we think forward?
In order to address climate change, we have to act now, in our time, and we have to do so with the future in mind. Are we capable of that? Can we imagine a future and bring it into being?
I sort of think of old trees as being these gifts, right? People don't make trees, they plant trees, right? And they cultivate trees. You can breed trees. The trees are not of us, right? Trees are very, very old. Plants are much older than animals. And if you think of gymnosperms, I mean, these are incredibly old genetic lineages. Anyway, so trees are not of us, but they are gifts to us. I really sort of believe that. They're ethical gifts, as well as intellectual gifts, as well as spiritual gifts. But they're gifts because they make us more human, because they allow us to really use our mental and emotional and spiritual faculties to their full extent.
Professor Farmer knows that human beings have some protective instincts when it comes to the natural world, from ancient trees to places like the Grand Canyon. He wants us to lean into those instincts and appreciate our time on Earth with the future in mind.
It's going to be a hotter world, but I want to hope that it can still be a fairer world. And the oldest beings of that world, they already exist. They're young trees now, but they can be old. So to think about not just future generations of people, but to think about the future oldest non-human things, the future elder flora, I just think that that is really exercising our full potential as humans. Trees are this gift that allow us to be fully human by living in time, in place, here on planet Earth.
This wraps up episode 7, Climate Change and the Problem with Time, and concludes season 3 of In These Times, Fear and Loathing and Science. The Omnia podcast is a production of Penn Arts and Sciences. Special thanks to Irina Marinov, Dmochowski, Jared Farmer, and all of our guests this season. In These Times Season 3 was produced by the Omnia magazine editorial team. Blake Cole, Lauren Rebecca Thacker, Susan Alborn, Lorraine Terrell, Brooke Seatonsons, and Evan Smith. Our theme music was composed by Nicholas Escobar, college class of 2018. Our logo design and episode illustrations were created by Dan Lee. I'm Alex Schein. Thanks for listening. Be sure to subscribe to the Omnia podcast by Penn Arts and Sciences on Apple iTunes, wherever you find your podcasts, to listen to all 3 seasons of In These Times.